Let us discuss static semantic embedding versus contextual semantic embedding. The static embedding models like word2vec and glow assign one fixed vector to each word regardless of the sentence in which the word appears in. They learn meaning from global or local co-occurrence statistics, so a word like a bank has the same representation whether it refers to money or a river. They calculate vectors of different words that means the same, which are mapped to close vectors. They do not perform same word means different at different context. At inference time, these models simply perform a lookup in an embedding matrix with no interactions between words in the sentence. In contrast, transformer models generate contextual embeddings where each word's vector changes depending on surrounding words in a sentence. They use self attention introduced in transformer architecture, allowing every word to dynamically attend to all other words in the sentence. You can watch my part 2 video on semantic embedding for more details. This means the representation of bank in a financial sentence will differ from its representation in a river related sentence. Structurally, static embeddings are shallow and context independent, while transformers are deep, multi layered architectures that compute meaning dynamically through contextual interactions. We will discuss how transformers used in bidirectional encoder, which is called BERT, refers to bidirectional encoder representations from transformers. We will discuss what is embedding from language models called MLO, and we will see architectural differences between BERT and MLO. We will also discuss evolution of other BERT architectures. Initially, we discuss BERT components. BERT first tokenizes text using a word piece tokenizer, and the word piece tokenizer builds a vocabulary of words and word fragments which are called possible subwords from the words. This is called token encoding. Then BERT performs segment embedding. It means BERT adds special tokens like CLS and SEP at begin and end of a sentence. BERT needs this segmentation to use for next sentence prediction. BERT uses position embeddings, which are learnable vectors that encode the position of each token in the sequence. This is explicit position embedding given to words. This process will be replaced by the positional encoder given in the transformers. Then each token is converted into a vector by summing token embedding, then performing segment embedding along with the position embedding which has learnable vectors. Please subscribe, like and comment for more series of technical videos on semantic embedding. After performing 3 steps on the input text, the word embeddings are fed into the BERT architecture. The BERT architecture has stack of multiple identical transformer encoder layers. It has either 12 layers for BERT base and 24 layers for BERT large. Each layer refines token representations using self-attention and feed-forward neural networks. The output of one layer becomes the input for next layer. As layers go deeper, tokens representation become more context-aware and semantically rich. For example, layer 1 to 3 focus on word relationships and short phrase relationships. Layer 3 to 6 focus on clauses in the sentences. Layer 6 to 9 focus on sentence semantics, and layer 9 to 12 focus on semantics of the entire text. If you go deeper, you get more semantically rich representation, and this needs to have more data and more computational power to train BERT parameters. You can add task-specific outputs for BERT models such as text classification or sentence classification. This task adds a fully connected neural networks followed by softmax layer or classification layer to text or sentence representation. If you want to perform token classification, then you will attach each token representation followed by fully connected neural network and a classification layer. For example, named entity recognition or part of speech recognition comes under this category. For question answering tasks, BERT takes input in the format question segmentation followed by a context segmentation. The model output contextualized embeddings for all tokens in both the question and the context. Two separate linear layers are applied to predict the start and end position of the answer span within the context. During pre-training, BERT uses masked language modeling (MLM), where a percentage of tokens are randomly masked and the model learns to predict the original tokens. This allows BERT to learn deep contextual embeddings and capture semantic and syntactic relationships between words. Let us discuss embedding from language models called ELMO. This is also a contextual word representation model. ELMO generates contextualized word embeddings using a deep bidirectional LSTM language model, where forward and backward LSTMs are trained separately and their representations are combined. Unlike BERT, ELMO produces embeddings that are typically used as features added to task specific models rather than being fully fine tuned end to end. You can see ELMO is shallow representation and sequentially connected, and it will be slow for training. Let us compare BERT and ELMO models' key operations. BERT uses a stack of transformer encoder layers with self-attention, allowing it to capture bidirectional context simultaneously rather than sequentially like bidirectional LSTMs used in EMLO. Additionally, BERT is pre-trained using masked language modeling and next sentence prediction, and it is fine-tuned as a complete model for downstream tasks, whereas ELMO mainly provides contextual embeddings for external models. ELMO uses next word prediction only and it is shallow model, whereas BERT is a deep model for contextual representation. Several variations of BERT have been developed to improve performance, efficiency, smarter pre-training, and better handling of span level information compared to the original BERT. Robot A is an optimized BERT that removes the next sentence prediction task and uses longer training with dynamic masking for better results. Albert reduces parameters using factorized embeddings and cross-layer parameter sharing while maintaining similar performance. Distill BERT and Tiny BERT are compact versions of BERT using knowledge distillation to create smaller, faster models suitable for deployment. Electra introduces a more sample-efficient pre-training method called replaced token detection, where the model learns to distinguish real tokens from fake ones generated by a small generator, instead of masking tokens like BERT. Span BERT improves on BERT for span level predictions by masking contiguous spans of text rather than individual tokens, which enhances its ability to model phrases and extract entities. Please subscribe, like, and comment for more such technical videos. Conclusions and key takeaways. BERT architecture is explained using transformers. Also discussed the sentence processing steps and key operations in BERT. ELMO architecture is discussed and compared against BERT. Various BERT architectures are discussed.